So let's go with this. Designing an experiment. So we've already talked about the basics of what's an experiment versus what's an observation. And now we're going to dissect how you design an experiment a little more closely. So let's actually, in order to carry through this, let's talk about an example. Let's pick up with the example that we had, that we ended last time with. Where we said if you drive a BMW, you live longer. Well, not really. In order to find that out, if that's really true, you'd have to do an experiment. So let's actually talk about how to do that experiment. And how to design that. So you want to find out the effect of which car you drive. The effect that has on your lifespan. And so you get a sample of 100 people, give 50 of them BMWs, give 50 of them Toyotas, and then you see what their lifespans are. Okay. So, in this experiment, what is the research objective? Right. Okay. So to see if people who drive BMWs live longer, or more objectively, to find out the effect of which car you drive on your lifespan. Okay. What is the treatment, or what are the treatments? Right. So, but for treatment, you have to say specifically what the treatments are. So, treatment number 1 is BMWs, and treatment number 2 would be Toyotas. Exactly. Right. Okay. So now I've talked about some new terminology and things. Factor. So in this case, the factor is what type of car the subjects drive. So a factor is really just is sort of a general description of what the treatments are, whereas the treatment fills in the details of what they're actually doing. So when you said what car they drive, that's the fact. That's really what the factor is. That's the thing that you're going to manipulate, and you're going to manipulate it into what? To BMWs, Toyotas. Those are the treatments. So the factor, if you like, you could think of it as just the general classification of input. What is it that you do to the general description of what you do to the subjects? And this is also called the explanatory variable. What is the response variable? Lifespan, absolutely. Response variable is the result that you're measuring, and the result that we're measuring here is how long they live. And you can think of that. You can think of the factor as the input and the response variable as the output. I'm a mathematician, so I like to think of this in terms of a function. Input, output. Okay. Okay. So, in general, what are the steps to doing an experiment? Well, this is sort of in the real world. If you're a scientist and you're like, I'm going to do an experiment. First, you have to say, here's what I'm going to do an experiment about. You have to identify the issue that you're going to study. Number 2, you're going to determine the factors that you think affect the response variable. So you're saying, I want to test a particular input-output relationship. If you think of the example that we talked about, I believe it was last time, you would say, does making a suggestion affect the type of ice cream that people buy? So you'd also decide you want to study that. Okay. 3, you determine the level or the treatments for each factor. So in this case, so if you look at the car example, you'd say, I wonder if which car someone drives affects how long they live. And then you have to say, well, which kind of cars am I going to have people drive? In this case, we made the choice to say some people get BMWs and some people get Toyotas. You could have made other choices. Those are the choices that we made. Also, the word level has a particular meaning. The levels are the different values each factor takes on. So I keep saying each factor. In this simple scenario, there's only one factor. So there's only one thing to talk about. Later on, we'll see an experiment that we design where there's a bunch of different factors, and we'll have to think about each of them separately. But in this case, there's only one factor. It's which car you drive, and so the quote-unquote levels of that are BMW and Toyota. Next, you have to determine the number of subjects, and we're actually going to do this from a computational point of view later in the semester when we start doing computational stuff. 5, of course, you conduct the experiment, and then 6, you reach a conclusion. You see if your claim is true or not. Okay, so this is the overall framework. So far, we've talked about let's see. Well, I guess we've discussed a couple of things. Like, for example, we've discussed how do you get your sample. But once you have your sample and you're trying to conduct your experiment, there's another important choice that you need to make. You need to decide, once you have your sample, which subjects are going to go through which treatments. So once again, you should try to do this in some random sort of way. You would never say, okay, now that I've gone through all this trouble of getting a very random sample, all the men drive BMWs, all the women drive Toyotas. That would be ridiculous. So once again, you've got to randomly assign them to these groups. Now, how can we randomly, once we have our, in this case, 100 subjects, how can you assign some to BMW, some to Toyota? Yeah. Oh, okay. Absolutely. Right. So we'd want to make sure that, for example, different groups such as different genders are equally represented for BMW in the BMW group and in the Toyota group. Absolutely. So that's really good, and that form of assigning subjects is actually called something. I want to get the first one out of the way. So the first way to do this is I have 100 people in my sample and just assign them completely randomly. For example, since there's only 2 choices here, have them flip a coin. Heads BMW, tails Toyota. So that's completely random, completely fair. 50 names from a hat, whatever. Okay, so Elizabeth, the one that you mentioned where you said, let's make sure that we have an equal number of men and women in both groups, that is a form of what's called randomized block design. Now, I'm guessing, you tell me if I'm wrong, I'm guessing that you got this idea of making sure that we had equal number of men and women, you were thinking about stratified sampling, where you want to make sure that you have different groups equally represented. This is similar to that, but again, stratified sampling occurs when you have your population and you're getting your sample. And that's one step in the experiment process. The next step is, once you have your sample, how do you assign people to each treatment? So that's a big difference that people often get confused. So doing that sort of thing, making sure all the, in this case, gender or race or whatever, is equally distributed among your different treatments, that's called randomized block design for the experiment. Okay. So here. So I wrote up one little example. I said, let's break up, because we decided that being a man or a woman is probably going to affect your lifespan. I think that on average women live like 2 to 3 years longer. And we decided that well, the problem with the problem with the BMW data is that rich people versus poor people tend to have different lifespans as well. So once we have our sample, take the group of rich men, however we define rich, give half of them BMWs and give half of them Toyotas. Take the rich women, give half of them BMWs and give half of them Toyotas. And in this way, you're trying to control these different variables, making sure instead of, as I talked about last time, we don't want the BMW owners to be on average richer. So in this way, you take the rich people and split them up half and half. Or more specifically, in this case, rich men half and half, rich women half and half, etc., etc. So the definition for this, again, is fairly similar to stratified sampling. Divide your sample into blocks of subjects who are similar according to certain characteristics. Then from each block, randomly assign subjects to each treatment. So for example, the way that I've written it out here, what is my first block from my sample? Yeah, the first block is rich men. So you take the rich men, and then you distribute them evenly among your treatment groups. Next, you take the rich women, etc., etc., etc. So notice that breaking up, taking your sample and dividing them among the treatments, doing it completely randomly should take care of pretty much everything. But I like to say, if you're a little more control freak, then maybe you do randomized block design. You want to make sure that the rich men are divided equally among the treatments. You want to make absolutely certain that the rich women are divided among the treatments. So these are two options. Now the third option, I like to say, is for the complete control freak, and it's called match pairs design. And what is match pairs design? You take your sample and you find two people in your sample who are as similar as possible. For example, perhaps in your sample you have a pair of 37-year-old men that would both be classified as rich. So once you have those two people matched up, what do you do with them? Exactly. One of them gets a BMW, one of them gets a Toyota. So, again, like I said, this is the control freakish way of making sure that your BMW group and your Toyota group are both similar samples, or both similar groups from your sample. Okay. So again, all three of these are ways of making sure that both groups are the same, except for the factor whose effect you want to measure. In this case, which car they drive. And just a reminder, sampling is starting with the population and selecting subjects. Assigning subjects is once you have your sample, choosing which treatment each gets. Okay. All right, any questions about this bit? Okay, so next thing. What I mentioned before was that in this case the design was very, very simple. You're only comparing two things. BMW, Toyota, what's the result? But for different reasons, you might want to deal with a slightly more complicated setup. So, for example, suppose you give subjects a combination of St. John's wort and ginkgo to see the effect on how much they sleep. So basically, suppose you're doing medical research, and you're testing out these different herbs and compounds to see if you can help people sleep better. So one of the first things you need to decide is, how much St. John's wort am I going to give people? Well, suppose you want to test these different possible amounts. So every person is going to get either of the St. John's wort, they're going to get either 0 milligrams or 10 milligrams or 20 milligrams. And of the ginkgo, you're going to give each subject either 0 milligrams or 25 milligrams or 40 milligrams. So the question is, what are the treatments? So if you take a subject, what's something that one subject possibly could receive? Right. We're giving them a combination of St. John's wort and ginkgo. Yes, combined. So what's one possible pill or dosage that we could give a subject? Give them how much?
35 or 50.
Okay. Well, don't say 35. 35 milligrams of sand. 35 milligrams. What is it? Which is what? 35 milligrams of St. John's wort? No. How much of the St. John's wort and how much of the ginkgo?
10 milligrams.
Okay. Right. I hope you pay more attention when you go to your doctor and he gives you pills. Right. 10 milligrams of St. John's wort and 25 milligrams of the ginkgo. That's one possibility. What's another possibility? 20 milligrams of St. John's wort and... Okay, what's another possibility? Okay, what's another possibility? Absolutely. Okay. So these are all possibilities. So how many different treatments are possible? Okay, so in a second I'll give you a very clever and straightforward way to answer this question. First, statistics. What are the factor or factors in this experiment? Right. The St. John's wort and the ginkgo are the factors. Now, for the St. John's wort, what are the different possibilities? Right, so there are three possibilities and they are 0, 10, and 20. Those are called, for St. John's wort, those are called the levels. The levels. Now, for the ginkgo, what are the possibilities? 0, 25, and 40. For ginkgo, those are the levels. So St. John's wort has 3 levels, ginkgo has 3 levels. And finally, the question we need to answer is, how many different treatments are there? We just listed off 1, 2, 3, 4 of them, and it turns out, well, I'll show you a pretty little picture and then maybe you can tell me how many different treatments there are. How many different treatments are there? Why? Yeah, 3 times 3. You see that based on the picture now? Okay. Right. Every possible combination represents a treatment, and if you draw it in using this box, it's very clear that the number of combinations is 3 times 3. 3 for the ginkgo, 3 for the St. John's wort. 3 times 3. Every box represents a treatment. So there you go. So notice that as soon as you have, in this case we have 2 factors, as soon as you have more than 1 factor, you really do need to keep track of what's going on. It's not as straightforward. Okay. And medicine is a really good example of a field in where you would use 2 factors, not just 1. Now, can you think of a common sense reason why that would be the case? Why couldn't we just test ginkgo separately? Okay, what are we comparing? Okay. Why is it important? Why couldn't we just test ginkgo separately and then test St. John's wort separately? Right. Okay. So why couldn't we test them individually? Okay. I would say that in the field of medicine, what happens when you take two drugs at the same time? Yeah. It's what's called an interaction. So, you ever read the warning label? It says if you're taking this drug, whatever you do, make sure you don't take some other drug. Individually, two drugs may be okay, but if you take them at the same time, they could have side effects or an interaction. Okay. So we would like everything to be very neat and nothing interacts. So if we test ginkgo separately and St. John's wort separately, you like to say, well, if one gives you an extra hour of sleep and the other gives you an extra hour of sleep, put them together, you get 2 extra hours of sleep. But it doesn't always work like that. So sometimes it's important to test not just one thing at a time, but different combinations. So what you might find out is that ginkgo by itself does nothing, St. John's wort by itself does nothing, but together they solve the problem. It's possible. Okay. So. Okay. So, and I want to go back and mention something from before. When we had, in the previous example of BMW versus Toyota for lifespan, we only had one factor. And we said there are two treatments, BMW and Toyota. We didn't say anything about levels. That's because it's a little bit redundant. When you only have one factor, which in that case was the car, what car you drive, the levels and the treatments are the same thing. Notice that with the St. John's wort and the ginkgo, you said each one has its own levels, and then we need to look at the combinations in order to find the treatments. If there's only one factor, there are no combinations. So we don't need to worry about finding combinations, which means levels, treatments, same thing.
There were different models of cars?
No, that would still be only one factor. You could put BMW, Toyota, I don't know, Hyundai, Honda.
I'm just saying, I'm sorry. Within the division of BMW, you have like a BMW 745 and a BMW 225. So you go to Camry, you go to Sienna, whatever.
Okay. So would you, okay, so this is a good question. Would you be looking at different combinations of cars?
Right.
Would you? So think about the previous example. You give someone a combination of ginkgo and St. John's wort. Would you give someone a combination of BMW and Toyota? No, so that doesn't make sense. You could say BMW 5 Series versus BMW 7 Series, but you wouldn't give them different combinations of car. You only give them one car. Yep. Good question. Okay. Alright, so any questions about this? Okay. So what we're going to do right now is I would like you guys to once again group up, and I would like say groups of probably about 4 or so, and I would like you to design your own experiment. So come up with a question that you would investigate, figure out how you're going to get your sample, and figure out all these different things. Figure out your treatments and all that. Okay. And then also figure out what experimental design you're going to use: random, randomized block, match pair, etc. So all the various things that we've talked about so far, try to design an experiment using all of them. Okay?